To computing performance, we were focused on classical computing based on the CPU. Classical computing is essentially the digital computer. Almost every computing device on the market today is a classical computer. Classical computers operate in serial. In other words, as mentioned in the first video in the series, Computing Origins, executing various instructions extremely fast in order. But to the average user, it appears to be running them in parallel, meaning multiple instructions at a time. This is due to many hardware and software optimizations to allow for asynchronous operation. By the end of this video, the distinction between parallel and asynchronous operation will become clear, but first let's see how classical computer works. As a disclaimer, the concepts we will be discussing are an overgeneralization of computing architecture, but for the sake of getting an abstracted understanding of classical computing functionality will serve well. Alright, so first let's bring in the central processing unit. The CPU is the brains of the computer. Let's also bring in memory, the RAM. This is where the CPU accesses stored information it needs. Now the CPU also has built-in memory. This is called a cache. The cache is considerably smaller than the RAM, with sizes ranging in the order of 32 kilobytes to 8 megabytes. The purpose of the cache is to give the CPU the information it needs immediately. The CPU and RAM are separate objects, so when the CPU needs information, it takes time, albeit a very small amount of time, to read the data from the memory. This time can add considerable delay to computer operation. With the cache being right on the CPU reduces this time to almost nothing. The reason why you don't need much cache storage is because it just needs to store little bits of important information that the CPU will need to use soon, or has been using a lot of recently. There are various methods implemented to determine what goes onto the cache, what should be kept on the cache, and when it should be written back onto the RAM. In a typical CPU, there are various levels of cache, each with different read and write times and sizes. For the sake of simplicity, we'll assume a single cache for our CPU. So now, with the basic components out of the way, let's get into how the computer operates. When a CPU executes an instruction, there are 5 basic steps that need to be completed. Fetch, get the instruction from the memory and store in the cache in some cases. Decode, get the appropriate variables needed for the execution of the instruction. Execute, compute the result of the instruction. Memory, for instructions that require memory read-write operation to be done. Write back, write the results of the instruction back into memory. Nearly every instruction goes through the first 3 and final step. Only certain instructions go through the memory steps such as load and stores, but for the sake of simplicity we'll assume every instruction requires all 5 steps. Now each step takes 1 clock cycle. This translates to CPI, clock cycles per instruction of 5. As a note, most modern processors can execute billions of clock cycles per second. For example, a 3.4 GHz processor can execute 3.4 billion clock cycles per second. Now a CPI of 5 is very inefficient, meaning the resources of the CPU are wasted. This is why pipelining was introduced, bringing asynchronous operation into computing. Pipelining essentially makes it so each step can be executed in a different clock cycle, translating to 5 instructions per 5 clock cycles, or in other words, 1 instruction per clock cycle, a CPI of 1. Essentially, what pipelining does is take the segmented steps of an instruction and execute them in each clock cycle. Since the segmented steps are smaller than the size and less complex than a normal instruction, you can do the steps of other instructions in the same clock cycle. For example, if a step for one instruction is fetching the data, you can begin decoding another, executing another, etc., since the hardware involved for those steps isn't being blocked. Superscalar pipelines add to this performance further. Think of pipelines as a highway. Now a typical lane in the highway can execute 1 instruction per clock cycle. With superscalar processors, you add more lanes to the highway. For example, a 2-wide superscalar, also referred to as a dual-issue machine, has a theoretical CPI of 1/2, 2 instructions per clock cycle. There are various other methods implemented to make the processor's CPI more efficient, such as unrolling loops, very long instruction words, VLIWs, which are essentially multiple instructions wrapped into one larger instruction, compiler scheduling and optimization allowing for out-of-order execution, and more. There are also many issues that come along with pipelining that decrease CPI, such as data hazards, memory hazards, structural hazards, and more. All these topics are beyond the scope of this video, but mentioned to satisfy curiosity if you wish to know more about them. So at this point, we now know about the basic design of a CPU, how it communicates with memory, the stages it executes instructions in, as well as pipelining and superscalar design. Now instead of imagining all of this as a single CPU, let's take it further. All of this technology can be embedded on a single core of a processor. With multiple cores, you take the performance of a single core and multiply it by the core count. For example, in a quad core by 4. Multiple cores also have a shared cache as a side note. The use of superscalar pipelines as well as multiple cores are considered hardware-level parallelism. The computer industry, after years of stagnation, is now beginning to divert more focus to hardware-level parallelism by adding more cores to processors. This can be demonstrated by consumer processors like AMD's Threadripper line and Intel's i9 processor line with core counts ranging from 8 to 16 and 10 to 18 respectively. While these may be their higher-end consumer processors, even the low and mid-end processors from i3, i5, and i7 are getting buffs, with core counts ranging from quad, hex, and octa-core. As a side note, supercomputers are the best examples of utilizing hardware parallelism. For example, Intel's Xeon Phi and AMD's EPYC processors have core counts ranging from 24 to 72, with supercomputers having tens of thousands of processors within them. Now there's one key component that is required in tandem with hardware parallelism to truly use all the resources efficiently: software parallelism. This leads us to the final topic in classical computing we'll cover: hyperthreading, also referred to as multithreading. Instead of being implemented as hardware parallelism, this is used as higher level software parallelism. Think of a thread as a sequence of instructions. Now with single threading, that sequence of instructions just flows through the pipeline as normal. However, with multi-threading, you can segment your application into many threads and specifically choose how you want to execute them. Multi-threading can significantly increase computing performance by explicitly stating what CPU resources you want to utilize and when. For example, for an application, the user interface, GUI, can be executed on one thread while the logic is executed on another. This is just one example of many instances where multi-threading can be used. Now, multi-threading can't just be used for every application. Since classical computing isn't intrinsically parallel, there can be a lot of issues with concurrency, or in other words, when multiple threads are executing at the same time but depend on the result of each other. Thus, some applications end up being only single-threaded. However, many individuals and groups are working on ways to best utilize hardware parallelism through new software practices and rewriting old software. For example, the latest Firefox updates now are bringing in multi-threading. Also, some of the most computationally intensive tasks by default excel at multi-threading, such as video editing, rendering, and data processing, to list a few. Also, as exemplified by the gaming industry, a lot of games are now moving into multi-threading performance. So in summary, classical computing is asynchronous, not truly parallel. Instructions are still executed in serial, but through the use of hardware and software level parallelism, maximize the utilization of the resources of the computer, making them execute extremely fast, giving the illusion of parallel operation. Also, if you want a deeper look into how the CPU works, I highly recommend you check out the 2 videos I've listed in the description below. At this point, the video has come to a conclusion. I'd like to thank you for taking the time to watch it. If you enjoyed it, please leave a thumbs up, and if you want me to elaborate on any of the topics discussed, or have any topic suggestions, please leave them in the comments below. Consider subscribing to my channel for more content, follow my Medium publication for accompanying blogs, and like my Facebook page for more bite-sized chunks of content. This has been Encore, you've been watching Singularity Prosperity, and I'll see you